everybody here, hopefully, for Computer Engineering 585. For the computer vision course, right? Hopefully. Okay. So let me give you an idea of what kind of course this is. And before I do that, hopefully everybody knows me. I am Professor Mahmood. Okay, email mahmood@bridgeport.edu. Okay, and my office phone, 203-576-4737. And the office is in Technology Building 220. Let's see if I can pick it. Okay, so as far as computer vision is concerned, this is, in my opinion, a very useful, very modern, very exciting course. Part of it will be standard image processing. Part of it will be the artificial intelligence component to it, how we create, how we do recognize objects, do intelligent detection in images based on the latest artificial intelligence and deep neural networks. So part of it will be very modern, very exciting. Okay. Anyway, so what we'll do in this course is, just to give you an idea, is start out with the basic image processing. Okay, that's as we do image processing, often, if the image is not very clear, we try to enhance it. So some of the enhancement techniques are basically applying filters. Okay. As I'll show you, there are different kinds of filters that we apply to images. Okay. Some of them are, standard filters like e.g. There's a filter called Gaussian filter as an example, right? Then we have another concept over here called convolutional filters. Okay, where based on some mathematical theory of convolution, we try to enhance the edges or improve the contrast in the image. So what I'll do is I'll give you the theoretical background, and then we'll come up with what we call a kernel, so that as we apply that kernel to the image, it enhances it in a certain way. Okay. So some of the convolutional filters are based on single derivatives. When we do the differentiation, the first order differentiation, and some of these are based on second order derivatives. So derivatives. Okay, so there are filters like Laplacian. Okay. Sometimes what we do is take a Gaussian filter, then do the Laplacian on it to enhance it in a certain way. So we have Laplacian of Gaussian as an example. Anyway, don't worry about it. As we go into more detail, you'll get a much better handle on it, how these filters are created, designed, and what kind of effect they give it to us on as we apply them to an image, right? Okay, so after learning some of the fundamental theory as well as programming it and learning these convolutional type of filters, both first order, second order derivative based filters, then we'll take a look at see, as far as vision is concerned, right? Vision is basically, as you can see, deals with recognizing objects or detecting objects. So there's a concept called object detection and there's a concept called object recognition. So what's the difference between the two? Okay, let's say we took a picture, right? And here's a picture of somebody, some face in it, there's some tree in it, some other, cloud or something over here, right? Okay, so if we wanted to recognize, is there a face in this picture? Sorry, if we wanted to not recognize, detect. So object detection will be, is there a face? So is there a face in the picture? Okay, so if it does detect a face, it will draw us, we may draw some kind of a boundary on it to say, okay, this is where the face exists, right? Okay, so after we do the detection, so generally the first step in any kind of vision processing is do the detection. Whether it's a face or whether it's a car, whether it's a bicycle or a tree or a fish, whatever we are interested in, we want to see does that exist in the image, right? After we have detected, for example, the face, then the second step is the recognition. Okay, who is it? Okay, so is it the picture of, let's say, Obama, or picture of some movie star, or picture of somebody who's a student, right? So who is that? So recognition basically means, in case of the face example, who's the person? Okay, so to give you an idea, over the years, different detection algorithms have been proposed and improved upon gradually. And over the years, different recognition techniques have been proposed and improved upon. Okay, so to give you an example, one of the most famous one of the most famous face detection algorithms like anytime you use a digital camera, you put it in, if there are people in the image, it will draw squares around the face of each person, right? So pretty much all cameras these days, they use a face detection algorithm, which is by two famous authors called Viola and Jones. And this is based on a technique called Haar transform based classification. Okay, so there's, I'll introduce what this Haar transform is, or some people call it Haar features as an example, H-A-A-R, okay. So one of the algorithms we'll study nicely in the course is how does Haar feature detection work? Okay, it can be applied to faces, it can be applied to detecting cars. So, if we wanted to set up a camera for the traffic to automatically detect a car, maybe they wanted to get an idea of how congested the road is, so how many cars are passing through a particular point. So a Haar feature detector could be created to start detecting cars and start counting cars, right? So anyway, as we go along, I'll talk about what is hard transform, how does it work, how does Viola and Jones algorithm works. Okay, and for a lot of the algorithms that we discuss in this course, what we'll do is, after we learn the theory, okay, for some of these algorithms, you'll program the base algorithm yourself, okay? For some of these algorithms, there's a very popular library, it's called OpenCV, CV for computer vision. Okay, so OpenCV library is from Intel. It's written in C++, but it has wrappers for Python and C#. So some of the programming, by the way, I forgot to mention in this course, some of the programming will be done in C#. Some of the programming will be done in Python, okay, but not C++. Okay, these two languages, in my opinion, are more productive than C++, and because we have wrappers available anyway, so no need to make our life harder. So this brings me to the next question. If you do not have a C# or Python background, will you be at a disadvantage? No, okay. As I go along, I'll present small examples. In fact, a lot of the beginning assignments that I'll give you my own C# or Python code that you will go through, you'll try it, and gradually get better at it. So as long as you know one language nicely, whether it's Java or whether it is C++, learning another language is really, in my opinion, doesn't take more than half a day if you're decent in programming. Okay, so don't worry about not knowing. C# is extremely similar to Java and C++ with a small syntax change. Okay, and with the examples I'll provide, you'll get better at it, right? Python is the easiest language in the world. It does get more involved as we go into more advanced composing of the code for computer vision, but by that time you'll be already gradually getting better and better at it, so no need to worry about that part, right? Okay, so anyway, you guys will be programming some of the assignments using the OpenCV library, either in C# or in Python, or sometimes both. Okay, some of the algorithms that I described, they are so important in my opinion that even though this library will give you a pre-created code, I'll have you create your own code from scratch so that you 100% understand how the algorithm works, right? Okay, so anyway, so that's a very conventional way of detecting objects like faces, like cars, like bicycles, based on the hard transform, right? Viola and Jones' original algorithm was proposed in 2001. Then they revised it, made it better in 2004, right? That's still 15 years old, okay? The way the technology is moving, 15-year-old is extremely old, okay? So what's the latest? Do we still use Viola Jones? The answer is yes, we still use it, but there is a better algorithm now. What is a better algorithm? The better algorithm is called YOLO. Stands for you only look once. Okay, and this is based on deep neural networks. So one of your assignments towards the end will be to program this from scratch. So even though there are libraries available that will, in 10 lines of code, you can see how the algorithm works and we'll start detecting it. But like I said, this is such an important and useful algorithm that I'd like you to program it from scratch. I'll explain each and every detail about the algorithm so that you know how to do it, okay? So anyway, that's the detection part. So like I said, in computer vision, generally, after we do the detection, then comes the recognition. Like if we are doing a face detection, then recognizing who that person is, okay? So for recognition purpose, let me show you some of the, we'll learn both the classical techniques as well as the most modern techniques. Okay, so as far as the classical recognition techniques are concerned, okay, for example, one of them is based on a mathematical concept called principal component analysis. Okay, very briefly, so this is, by the way, abbreviated as PCA. Okay, PCA is a very important algorithm. Even though if you wanted to do recognition, you will not use PCA these days. But for analyzing data, not from the purposes of recognition, but for the purposes of getting more insight into the data, PCA is an extremely important algorithm. So you'll be programming PCA from scratch. Okay, I'll explain all the theory. And very briefly, the way it works is, see, if you take a look at, let's say we wanted to recognize, given a picture, so given a picture like this, over here, we do the face detection. We cut out the face, now we have the cut out face, right? So now we wanted to know who is this? Okay, let's pretend, rather than you guys using your card to go to the gym, okay, what if there was a camera? As soon as you walked in, it took your picture, automatically detected, are you a registered student at UB, and let you in or not, right? Okay, so so the question is, how do we do the recognition, okay? So let me give you an idea. So before we do the recognition, let's take an example of a time signal. Okay, suppose this is time. Okay, and let's take a look at a simple sine wave. Okay, so here's a sine wave. Okay, and your goal was to design a system so that you can recognize what kind of sine wave it is. Okay, so one option is you take samples of this wave in time. Okay, so let's pretend every millisecond you note down what's the value. Okay, value is 0, so this is the value. Time is on the x-axis, on the y-axis is the value, right? Then 1 millisecond later, you measure the voltage again. Let's pretend it is 0.2 volts. 1 millisecond later, you measure the voltage again. Pretend it's 0.4 volts, right? So basically, you're given some data, like 0.0, 0.2, 0.4, 0.6, 0.4, 0.2, and so on. So you're given a sequence of numbers, okay, which are basically samples that you took on the wave. And by looking at this, your goal is to predict if it is a sine wave or if it is not a sine wave, okay? So let me show you the problem with measuring data in the time domain, okay? What will happen, let's say somebody gave us this sine wave and we looked at the pattern. Oh yeah, so let's say our stored data is also 0.0, 0.2, 0.4, 0.6, 0.4, okay? So this is our incoming data. So if we wanted to know, is it matching our stored data so that we can claim it's a sine wave of this particular type? Okay, so one way you will do it is, every sample you take, you'll compare it. So and compute the error magnitude. So the error magnitude will be incoming data is 0, stored data is 0, you subtract it, square it. Then you take a look at the second sample. Incoming data is 0.2, stored data is 0.2, you subtract them, square, plus 0.4 times next sample minus 0.4 square, and so on. Okay, so what will be the answer in this case? 0, right? So if the error is 0, what does that mean? It's a sine wave. Okay. Now what will happen? Our stored data is like this, but the incoming data happens to be a little bit shifted in time. So it's still a sine wave. Okay, it's still the same type of sine wave, but our first sample is negative 0.2. Our next one is 0. Next sample is 0.2. Okay, so now our incoming data is negative 0.2, 0, 0.2, 0.4, 0.6. Okay, if we computed the error, what will it come out to be? Will it come out to be 0? No. So as you can see, tiny bit of time shift makes it not recognize that it's a sine wave. It produces a huge error, right? Okay, so same thing with if you take a look at the images, right? If we wanted to recognize who this person is. Okay, so first of all, the images are nothing but two-dimensional array of pixels. Okay, what exactly is a pixel? So let me show it to you. Okay, a pixel is like a dot. So let's say you take a picture. It's 100 by 100 pixels. Every pixel has 3 components to it. A red component, a green component, and a blue component. Usually we use 8-bit color. In an 24-bit color, with 8 bits for red, 8 bits for green, 8 bits for blue. So if we have 8 bits per color. Okay, so then our range will be 0, 0, 0 to when every bit changes to 1. If I convert it to binary, a set of 8 zeros is 0. What is a set of 8 ones? If I convert it to binary, anybody remembers? 255. So each pixel is basically 3 numbers ranging from 0 to 255. So let's pretend the background over here is white color. Okay, if the background is white color, the pixel values will be 255, 255, 255. Okay, because if everything is maximum, it produces a white color. Let's pretend at some point in time there's a yellow color over here in the background. See, red and green together make yellow color. So the value of the pixels will be 255, 255, 0. Okay, so anyway, if we have a color image of a person, it will basically be 3 matrices. Each will be a 100 by 100 matrix. The first matrix will be set of values. So let me show it to you. Okay, so here's a 100 by 100 matrix. Okay, so there will be a red channel. There will be another 100 by 100 matrix for the green channel, and another 100 by 100 matrix for the blue channel. Okay, so whatever each pixel value for the red part is, so if the red part is 255, 255, let's say 200, and so on, 80. So anyway, there will be a bunch of numbers, 100, 120, 211, 95, right? So basically there will be a set of 100 by 100 numbers representing the red color. There will be a set of 100 by 100 numbers representing the green color. Pretend this is 200, 190, and so on. 111, right? Very similarly for the blue color, 210, 80, 197, right? So given a picture, we'll basically have, for this person, once again, if it's a 100 by 100 image, we can represent the image with 3 matrices like this. Okay, so let's pretend this is person X. We took a picture, we took a look at the red channel, green channel, blue channel. So person X could be, some movie star or one of the students at UB. Okay. Anyway, this is their data. So let's pretend we store this data. So this is our stored data for person X. Okay. Now let's pretend okay, so let's pretend over here, here's a camera. Okay, some person walks in. Okay, the camera takes the picture. And our code that we wrote in Python or C# or C++ or Java converts this image into 3 matrices again. Okay, and let's pretend this is person X, exact same person X. Okay, whose data we already had stored it in our database. Okay, so if this image is 100% same over here, then as you can see, we'll produce the 3 matrices, which will be identical data over here. Okay, so for example, the third matrix, I put 197 over here, so there will be 197 over here. Okay, so if we wanted to recognize, is this person X, what will we do? We'll go to each data point and do what? Compute the error. And the error is referred to as the Euclidean distance. So Euclidean, I hope I spelled it right. Distance. Okay, Euclidean distance is basically if you are given x1, y1 point, x2, y2 point, right? 2 data points. Euclidean distance will be x2 minus x1 square plus y2 minus y1 square square root. Okay, so this is what we call the Euclidean distance, which previously I mentioned was the error, right? Okay, Euclidean distance in the technical terminology is also called L2 norm. So if anybody says, compute the L2 norm, or compute the Euclidean distance, or compute the least squared error, they're same things, meaning you subtract one data from the other, square it, sum it, take the square root. Okay? So that basically tells us how similar or how different the 2 data points are in a high dimensional space. Okay. Anyway, so let's pretend, let's go back to my example. We took picture of person X. We computed the RGB channel values, stored them in 100 by 100 matrices. So this is our stored data, right? Now, somebody comes in. Let's pretend it's the same person X. If this image was taken, we did the face detection on it. Okay, and if this was perfectly aligned with this one, then as you can see, we'll produce the exact same matrices. And if we did the Euclidean distance between the 2, what will it come out to be? 0. But what's the probability of that happening? That this was 100% same. What if this is off by 1 pixel? If it's off by 1 pixel, okay, for example, let's go to the second one. Okay, it will be some number in the beginning, let's say it's 180. The second number will be same as this one because it's 1 pixel off, then 1 pixel off, right? If every one of these is 1 pixel off, will it produce a 0 error or a high error? A high error, right? Okay, further, it's not just the accuracy of the face detection that it not capture the face perfectly. Okay, what if the distance between the camera and the face is not the same when we recorded it? Okay, if the distance is even a millimeter off, it will be off by a pixel. Okay, so one of the concepts that I'll keep emphasizing it is when we try to recognize things in the signals world. Okay, so I'll keep contrasting our image world to signals world. Okay, like I gave you an example of a sine wave. Okay, so we were talking in the signals world, we have two concepts. We have a concept of time samples, and we have a concept of a frequency. Okay, so let me go back to my example of a sine wave. Okay, here's a sine wave. Okay, we were taking samples every 1 millisecond. Okay, so those were the concept of time. And as we discussed, if we compare two signals in the time domain, what will happen if these samples were a tiny bit off? It will not recognize it correctly, right? Now, let's go back to our same example of the sine wave. Let's pretend this is a sine wave of 60 hertz frequency. Okay, and let's pretend we develop the code which takes a look at the sample data, but rather than interpreting it as a value of 0.2 or 0.4, it tries to extract the frequency from it. Okay, and the frequency it extracts is 60 hertz when we gave it this data, right? So now we store it at 60 hertz. Okay, now let's pretend incoming signal is a little bit off, okay, just like previous example. Okay, but it's the exact same frequency. Okay, see, the time shift does not produce a different frequency. However, like this compared to this, these are different frequencies. But if it's same thing as time shifted, okay, these two are the same frequencies. Okay, so rather than comparing things in that time domain and computing the Euclidean error or Euclidean distance